So today I'm going to, or this afternoon, I'm going to talk to you about concrete dam foundation risks. So our objectives for this lecture are to identify key geotechnical foundation potential failure modes for concrete dams, identify foundation discontinuities and discuss how they relate to the foundation sliding stability, and discuss key factors for foundation sliding stability analysis. So here's a list of potential failure modes related to stability of a concrete dam. The first is sliding along a weak plane in the foundation or at the concrete rock contact, or a rock wedge formed by adversely oriented discontinuities, which results in displacement in the dam foundation or abutment, and I'll have some examples of that. Failure through the abutment rock mass, irregular or differential deformation, leading to stress concentrations that lead to that exceed the structural capacity, so basically cracking the dam itself. And then failed drains or increased uplift conditions in the foundation. That's often a contributor to the failure modes that I listed above, and solution features in soluble rock. And in addition, we consider failure modes related to erosion and scour during spillway flows or overtopping that could result in sliding stability issues. So I have a couple examples of Gibson Dam overtopping in the upper right. And then we also consider landsliding into the reservoir can also cause a wave that may overtop the dam. And Viant Dam in Italy is an example of this type of failure, although Viant Dam actually did not fail, but the wave in the reservoir caused by the landslide did result in life loss. So here's a list of historic failures of concrete dams. And the main point of this is to point out that the majority of historical concrete dam failures have been the result of foundation deficiencies and poor performance. So for concrete dams founded on rock, sliding on discontinuities within the foundation rock mass is the leading cause of historical failures. So therefore, in addition to the rock units, it is important to understand the type, location, orientation, distribution, continuity, spacing, and characteristics of the discontinuities within the foundation rock mass. Also point out that overtopping failures in all likelihood resulted from foundation erosion and undermining, and uplift failures and spillway failures could also have initiated by foundation problems. And then last, the only concrete dam known to have failed due to an earthquake was the Shikong Dam, which failed due to a co-seismic ground displacement during the 1999 Chichi earthquake in Taiwan. Okay, so I'm going to touch on a few case histories. So there are a number of notable failures of concrete structures that we should attempt to learn from and understand so that these triggering mechanisms and conditions can be applied to our risk assessments. So Austin and Bayless dams failed due to foundation sliding. St. Francis and Malpasset dams failed due to abutment deformation or block failure. And Camara Dam failed along a shear due to erosion of material from that shear. So I'm going to provide you some more details about the Malpasset Dam failure and the Bayless Dam failure. So a notable arch dam failure was the 217-foot high Malpasset Dam in southern France. The dam was 5 feet thick at the crest and 22 feet thick at the base. The dam was founded on massive gneiss in the right abutment and fresh to altered and sheared schist in the left abutment. Faults in the foundation strike parallel to the axis of the dam and dip upstream and perpendicular to the dam axis and dip steeply downstream into the left abutment. So there's the faults in the right picture. So there was blanket grouting performed at the dam foundation contact, but there was no grout curtain or drainage installed to control seepage through the abutment, and no instrumentation other than survey monuments were provided. A series of rainstorms filled the reservoir quickly in the late fall of 1959. On December 2nd, the dam collapsed suddenly. The flood wave caused total destruction along an 11-kilometer course to the Mediterranean Sea, and the number of deaths attributed to this failure was 421 people. So the only explanation that seems to be consistent with all the known facts and observations is that failure was caused by sliding and slippage on a upstream dipping fault plane that formed a rock block in the left abutment. So this diagram shows that fault plane. Large uplift forces developed on an upstream foliation shear for one of the several reasons or combination of reasons. First, the stresses generated in the rock by the arch thrust extended to great depths on the left abutment due to the orientation of the fault, decreasing the rock permeability for flow in the downstream direction. And tensile and shear stresses at the upstream face opened the foliation shear and allowed water pressures to easily penetrate to great depths. So basically, the force on this dam caused any jointing downstream to close and jointing upstream to open, and so water was able to get in basically on extra pressure to the dam. In addition, there were clay materials along that downstream shear that also created a dam that increased that force. So as the reservoir water rose, the loading increased until the rock block began to move. The arch tried to redistribute the loads higher to the thrust block, but under the extreme overload, that block moved about 3 feet downstream, separated it from the abutment, and without anything placed to transfer that load, the entire left side of the dam lifted and then rotated downstream until the dam ruptured. So it basically just lost its support and just slid downstream. So some questions that were posed by this failure is, could we get similar issues triggered by an earthquake? Could this failure rupture through a poor rock mass rather than those faults? Or would foundation drains have changed the result? So the second case history I want to share is Bayless Dam, which was constructed in 1909 in Pennsylvania. The dam was a 50-foot tall concrete gravity dam. The dam was founded on horizontally bedded sandstone with interbedded weak shale layers and was anchored 5 to 8 feet into the foundation. And there were no foundation drains. Hopefully you might see a pattern here. In 1910, after the reservoir filled rapidly, the dam slid downstream on its foundation, deflecting 18 inches at the toe, and 31 inches at the crest, and cracked in several places. This divided the dam into 5 or 6 separate sections, but amazingly, the dam did not fail. So in the upper picture, you can tell that the dam was straight. Right here in the part near the spillway with 12 feet downstream. So the dam did remain anchored to the foundation rock. However, the foundation rock was poor and the rock layers slid over each other. So the reservoir was lowered, and the partial failure was attributed in part to the concrete did not have time to reach ultimate tensile strength, and water was able to get under the dam and increase the uplift force on the structure, which reduced that sliding factor of safety and allowed the foundation to slide on itself. Engineers recommended repairs to the dam, but the reservoir was allowed to partially refill and eventually rose to just 2 feet below the spillway. The owner decided that the dam was sound and none of the recommended repairs were made, just based on the fact that the dam was fine, he thought, with just 2 feet of water, or the feet of, with the reservoir just 2 feet below the spillway. So in 1911, the dam filled again, this time to a 1/2 inch below the spillway crest. Leakage through and under the dam was widespread and increasing rapidly. The mill superintendent refused to open the outlet works and lower the reservoir because he felt maximum water level was needed to optimize the mill's productivity. But in that afternoon, the dam collapsed suddenly, destroying the towns of Austin and Costello, and 78 lives were lost. So I'm going to talk about potential failure modes that are related to fractures in the rock. So perhaps the most critical area for evaluating the foundation of a concrete dam has to do with sliding along adversely oriented geologic discontinuities within the abutment or the foundation of a dam. Planes or intersections that daylight downstream and form blocks upon which the dam rests should be identified and evaluated for sliding stability. This is shown schematically here how this could occur and the forces that typically need to be considered. So first, 3 or more geologic discontinuities must exist in proximity to each other. The discontinuities or combination of those discontinuities must be long enough and continuous enough downstream to interact with one another to form a discrete block. And the sliding surface must daylight in the downstream slope. So there's the block that could slide out. We also need to configure and constrain the geometry of the loading vectors and the sliding direction. The shear strength of the discontinuity surfaces providing resistance to sliding must be overcome by a combination of the dam water pressure and seismic loading. The configuration of the foundation must be considered. And so deeper socketed foundations result in significantly larger wedges and larger resistance. Shallowly socketed foundations can form smaller wedges with less resistance. And then the configuration of the downstream topography must be considered. So a ridge downstream forces the wedge to be larger and have more resistance, or a drainage swale downstream will cause a smaller wedge with less resistance. The light was on, but it just doesn't seem to work. Here's an example of Finding and mapping critical discontinuities on old construction photographs, including a shear plane and shale bed that were also mapped on the downstream abutment. These planes form potentially unstable blocks within the left abutment of the arch dam. So it is important to portray the geologic information on plan maps, sections, profiles, and structural contour maps so that the geometry is well understood and appropriate evaluations and calculations can be made. The only way to communicate these 3D systems is to the risk assessment team and decision makers is by developing these figures. We should develop new and updated maps and sections if the ones available are not positioned in the correct place to show what is needed. So here's an example from Bull Shoals Dam in northern Arkansas. Here the dam is founded on bedded dolomite that is generally described as horizontally bedded, but through review of the design drawing, there is a small dome structure in the rock, and that's represented by these contour lines in this picture. And this cross section, I didn't put the line, but the cross section basically goes right through that dome, and you can see that the bedding is dipping upstream and daylight's right at the top of the dam. So this is a potential sliding plane that could daylight right at the toe of the dam. Here's another example. This is John Martin Dam. So here the bedding is actually horizontal, and it does not daylight at the toe of the dam. So for the dam to fail here, there needs to be either a break in the rock downstream, or the rock at the toe of the dam would have to be eroded out. And we actually evaluated this failure mode a few weeks ago in Denver, and we considered possibility of scour at the toe of the dam. So the diagram in the upper right here shows a two wedge sliding analysis that is typically performed for concrete gravity dams, particularly when founded on horizontally bedded sedimentary rock. So the traditional 2D gravity dam stability analysis usually involves a passive block downstream of the dam. Although this type of analysis can be found in many guidance documents, it can be misused. So for one thing, unless the passive block is very thin, it is unlikely that shearing will occur through the rock mass unless the intact block material is very weak or there is an adversely oriented discontinuity through going within the passive block. So in addition, in order for the passive block to move, shearing must occur along the boundary between the active and passive block. Unless there is a near vertical joint or discontinuity in location, this is unlikely. So when I'm describing this is the passive block, and this would be, you would need a vertical joint there to allow those to be able to move out from each other. So here's a list of important foundation parameters that we need to understand to inform the stability along a failure plane. So are the discontinuities that would form a sliding plane continuous relative to the foundation and weak in shear? So we characterize the joint patterns in the rock by understanding the orientation, continuity, spacing, alteration, infilling, weathering, roughness, and small and large scale undulations. So that generally a block will slide more easily if the slide plane is in an orientation that will allow movement, is continuous, the sliding surface is smooth, planar, or contains infilling that will make it easier to slide. So the shear strength on a sliding plane is a critical factor for calculating the stability of a block. So the shear strength represents the capacity to resist forces that cause sliding along the discontinuity. So we want to think of this as like friction. So the shear strength can be estimated through laboratory testing and is dependent on the roughness of the discontinuity and the thickness of infilling within that discontinuity. So the strength of the rock at the contact and continuity of this discontinuity. So if the fracture doesn't propagate all the way through, that will increase that strength. So a phenomenon that is often misunderstood and overlooked concerns scale effects for rough joints and discontinuities. So when we test rock specimens for shear strength, we're testing core that's like 3 inches, but we're evaluating the a dam that's, hundreds of feet wide. So Bandis and Barton tested large rough joint specimens in direct shear, and then they cut them up into smaller and smaller specimens and repeated the testing. So as you can see from this plot, the average strength increased as the sample size got smaller. This is because at a large scale, the small scale roughness is not engaged as the sample is dilating in the test. But as the sample becomes smaller, that small scale roughness comes into play and dominates that strength. A common way to address this is to actually cut the sample with a saw and to test it. But that can underestimate the strength because of the sawing action might polish the rock. So alternatively, we started to remove that roughness factor mathematically by measuring how much it dilates when it's being tested in shear. So I'm going to touch on foundation uplift pressures. So foundation drains are installed in concrete gravity dams to reduce uplift pressures and increase their stability. So notable failure of concrete dams that did not have foundation drains are Malpasset, Bayless, and St. Francis Dam, which so foundation drains are typically considered the first line of defense against foundation instability. So measurements at several large concrete dams show that the pressures downstream of a line of functioning drains are greatly reduced by the drainage and often by the rock itself, as shown in the figure on the right. So the red line represents the theoretical uplift from the upstream heel of the dam to downstream. And then the blue lines are the actual foundation pressure measured. It's slightly counterintuitive because 100% uplift is on the bottom, 0% is at the top. So this blue line shows a decrease in the foundation pressures. So one problem is iron bacteria and calcium carried in the drain flow can result in blockage of the drains. So it's important that we keep the drains clean and efficient. The right image shows high pressure drain cleaning being used to clean the foundation drains from a concrete dam gallery. And then these pictures show how adding or cleaning drains affect the uplift pressures on the dam. The red line represents uplift pressures before adding or cleaning the drains, and the blue and green lines are after adding or cleaning the drains and show a substantial reduction in uplift. So I'm going to touch quickly on grout curtains. dams usually have a foundation drains, but then they have an upstream grout curtain. We cannot solely rely on grout curtains because we generally cannot get complete closure in our grout curtains, and just a small percent of opening can result in a significant amount of pressure that is able to get through. Okay, so I'm going to touch on 3D effects for foundation stability. So 2D stability analysis only considers sliding along a failure plane in a 2D cross-section. In 3D, there are factors that will make it more difficult for a monolith to slide out. And one of these is the joint orientation in the foundation. So a concrete dam will tend to slide in the downstream direction along monolith joints. So if the foundation rock has an orientation that differs from the orientation in the monolith joint, multiple rock blocks and multiple monoliths will be engaged, making it more difficult for the monolith to slide out. So this requires some shearing in the rock. And so I thought of this last minute, but here's a demonstration quickly. The orange blocks would represent the monoliths of the dam. The colored blocks represent the foundation. The prominent joint orientation is not parallel. So if I have movement of this middle block, in order for it to slide out, multiple blocks in the rock foundation has to be engaged. And part of that reason is because the monoliths are often bonded to the foundation, so otherwise they would have to slide on top of the foundation. So these examples here are from John Martin Dam and Bushels, and these colored lines represent how the joint orientation differs from the monolith orientation. So I'm going to go through this very quickly. Another consideration for 3D influence on stability is the shear strength along the monolith itself. Some monoliths are designed with shear keys to increase that strength. We also, from the differential movement between the monoliths and the foundation, we can get rotation that can actually cause the blocks to lock together more. Okay, I just have a few slides left on foundation rock modulus. The rock mass modulus is a parameter that describes the rock mass stiffness and resistance to deformation. In other words, it represents how much the rock will deform under stress. So differential foundation deformation between rock types can lead to severe cracking of the concrete in a dam. So if you think of the layer cake yesterday, if you have layers of the cake that are harder than the soft creamy layers, that cake was laying on its side, you put a dam on it, the softer part will let the dam deform and you can get cracking in the dam itself. So the foundation modulus is affected by the fracturing of the rock. The most direct way to estimate the foundation rock mass modulus is to measure it under large-scale jacking tests, but this is not done commonly in the US. But the modulus can also be determined by empirical relationships. So the easiest is to use the rock mass rating, which is based on intact rock strength, rock quality designation, joint spacing, condition of the joints, weathering, infilling. These are the same parameters that we were looking at yesterday when considering erodibility of the foundation. Also, the simplest way is the geologic strength index, where we can qualitatively look at how blocky the rock is and the condition of those joints to assess that. So this slide shows the factor of safety calculations for 3 foundation blocks in the foundation of a thick arch dam formed by upstream shallow dipping bedding planes, discontinuities, steeply dipping back release joints, and near vertical continuous side joints. An uncoupled analysis was performed using loading calculated from a 3D finite element analysis. So the foundation consists of variable foundation rock units and modulus values, with stiff assumptions being roughly twice the soft assumptions. So it can be seen by the factors of safety in this table. Lower factors, for softer modulus case, the dam deflects more and additional load goes into the arch action, which has a stabilizing effect of putting more normal stress across the side planes. So this can make a big difference if the factors of safety were lower, or when calculating probabilities of factors of safety less than 1. So it can be kind of counterintuitive, but in this case, the soft provides you better stability. So I think I'm running over time. So I'm just going to summarize this quickly. Most historical concrete dam failures are related to foundation deficiencies. Foundation analysis requires understanding of the geologic properties in the foundation. 3D geologic site characterization is useful early in the risk analysis and should gradually be increased as more information is needed. And then I'll just highlight the importance of considering 3D effects contributing to the resistance of a foundation wedge system.